Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. We have a liftoff. Liftoff on Apollo 11.
Shadow. 4 forward, drift into the right a little. 30 seconds forward, drift. Contact light. Okay, engine stop. Tranquility Base here. The Eagle has landed. Roger, Tranquility. We copy you on the ground.
So the name of the game today is Infinite Series. The goal is to determine whether or not an infinite series converges. And we're going to have that goal in mind for the next several sections, actually. So some definitions to get us started. You guys have seen, of course, having Calculus 1, you've seen this notation. Sigma or summation notation. Sigma is the Greek letter that you see there. It's a capital uppercase sigma, right? There's a funny looking E. Look, it looks like an E. It's an uppercase Greek sigma. And we say the sum from n equals 1 to infinity of a sub n. That is shorthand notation for a1 plus a2 plus a3 plus ... It just keeps going. There's an infinite number of terms there. So it's called an infinite series. So this is called an infinite series. So the nth, that's number one, and then number two, the nth partial sum. The nth partial sum of an infinite sequence. Okay, so I haven't shown you this notation yet, but this funky looking notation, the a sub k inside the curly brackets with the lower bound, k equals 1, the upper bound, infinity is just a shorthand for saying, hey, we've got an infinite sequence, a1, comma a2. We're not adding yet. It's a sequence. We don't add sequences. And then you just keep going. It's a shorthand notation. That funny-looking curly bracket notation is a shorthand notation for denoting an infinite sequence. And then if you want to find the nth partial sum of that infinite sequence, then that just means, we'll call it Sn. That just means you're going to sum the first n terms. So it would be, in summation notation, it would be the sum from, we could use I or we could use K. It doesn't matter. I'll switch to I. Just be aware that this is really that this guy right here, it's an index. It's a dummy variable. It could be I or K. If I want to be more consistent, I suppose I'd call it K. But I think in the notes I called it I, so I'll stick with that. So it's the sum from I equals 1 to n of a sub I, which is equal to a1 plus a2 plus a3 plus ... plus an. It's a summing. The nth partial sum of an infinite series is the sum of the first n terms. That's all we're saying. You just have to get used to the notation. And you have to get used to the fact that n is being used in two different ways here. And your book does this, so I stuck with it. Here, when you write the summation notation for the infinite series, n is the index, right? N is the index in that summation notation. When you talk about the nth partial sum, the n really means, the nth guy that you plug in, the nth input. And so n is taking on two different roles here, and it's something books do. You just have to get used to it. Okay, so note number 3. This idea of the nth partial sum of an infinite series allows us to think of a series as a sequence. And that's what note number 3 kind of tells us, at least implicitly. So note number 3, or definition number 3, the sequence of partial sums is denoted by this notation. So this notation would indicate S1. S2, it's really a set. S3, and then you keep going. S1, if you think about it, S1 would just be the first term in the series, A1. S2 would be A1 plus A2, the sum of the first two terms in the given infinite series. So what would S3 be? So
Plus A2 plus A3.
there you go. A1, whoops. A1 plus A2 plus A3. And then S4 would be the sum of the first four terms in the series and so forth. So that S1, S2, S3, dot, 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 that's a sequence. It's a sequence of summations. And why is that useful? Well, we've got some theorems that we developed yesterday involving sequences, and so we can apply them to series as well. So, okay, some more definitions and terminology, really. Number 4, if Sn, okay, Sn would be the nth partial sum, A1 plus A2 plus A3, dot, 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 plus dot, 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 plus An. If you think of that as its own sequence, so I left off the curly bracket notation here. But if you think of that as a sequence, the nth term of a sequence, Sn, if that converges to a real number, say S, we say the related infinite series converges to S. So think about it this way. This infinite series, assuming it converges to S, is really the limit as n goes to infinity of Sn, the nth partial sum, which we're saying equals S. That's the proper way to write that. So, I mean, this notation's nice, you guys. But what does it really mean? The summation notation's nice, but when you put an infinity on top of that sigma, what does that really mean? We're trying to make the definition rigorous instead of just saying A1 plus A2 plus A3 plus dot, dot, dot. And the idea is you define the idea of the nth partial sum, and you say, oh, if that infinite series converges to an actual number and doesn't go off to infinity or something, then you can say, oh, okay, then that would be the limit as n gets bigger. The number of terms we sum gets bigger and bigger and bigger, right? And so that's a way to kind of wrap our hands around what an infinite series really means when we say it equals a number. So we will say that this guy equals S, but does it really? Or is that just a convenience? Can you ever add an infinite number of numbers? No, you can't do it, right? So saying it equals S is kind of ridiculous. But we do it because it's just easier than saying it converges to S. But this is the real meaning of saying it equals S. Because the Sn is finite for any n, right? So saying that the limit of Sn as n goes to infinity converges to S, that allows us to use our limit laws that we have for sequences. It allows us to use all the machinery we've developed for sequences on infinite series. And really nail down what it means to say A1 plus A2 plus A3 plus dot, dot, dot. Okay, so this stuff that doesn't seem important, this notation, kind of seems like, yeah, whatever. It's really important. And later on it becomes even more important if you go on in math and study analysis. Find the first three partial sums of an equals 1 over 2 to the n minus 1. The first three partial sums, that means S1, S2, and S3. So can you tell me what S1 would be? Okay, in general, what is it? A1. Okay, in particular, for this nth term, or this sequence, if you think of it as just a sequence, using that nth term formula, what would you get for A1? 1, right? You're plugging in 1 for n right there. 2 to the 0 is 1, so 1 over 1, which is 1. Okay, S2 in general, what's S2?
A1 plus A2.
A1 plus A2. Oh, okay, so we can take the A1 that we already calculated, right? So that's A1, and then what's A2 going to be? 1 over So just use this formula to find A2. What do you get?
1/2.
1 over 2. And then S3, you guys do S3 for me. And you can use what we already have. In general, it's A1 plus A2, which we know, plus A3. So figure out what that would be. You don't have to do the arithmetic if you don't want to. Just, what would the next term be? I heard it. So what do you get?
1/4.
Oh, but you need other stuff.
1 plus 1/2 plus 1/4.
1 plus 1/2 plus 1/4. There you go. Does everybody understand what SN denotes? That's really important. Any questions on that?
Sn is the sum of NAs.
Yeah, so it would look, if you want to write it out longhand, it's not hard. You would just go A1 plus A2 plus, well, you'd have to put a dot, dot, dot in there, right? A3 plus dot, 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 all the way up to the nth term, whatever that is, whatever n is, when you plug it into the formula.